All set? Welcome. My name is Sam Elston. I'm from Innova International, and I'll be presenting this morning with my associate, Sri. Just to give you a little bit of background about myself, I've been a DB dev, a data architect, a consultant for various companies over the past 20 or so years, working with a lot of different types of databases along the way. I actually started off working with Oracle and Sybase, spent a lot of time with SQL Server, then got into MarkLogic and Cassandra and Postgres, and even a little bit of Redshift and Snowflake. So I like data. I love databases. Kind of my professional compass is I'm always trying to find ways to take current technology and apply them so I can transform data into useful information for our customers or for our clients and help our companies make money. And usually that involves a lot of fun tech stuff along the way. So that's just what I enjoy doing. Innova International's a Chicago-based financial company that focuses on online lending and analytics as a service. The part you'd be more interested in is their tech stack. They're very Postgres heavy. They're almost exclusively a Postgres shop. Their production environments have some 300 clusters, 500 so databases, with a number of our systems in the terabyte range. We have one app that's actually almost 10 terabytes. We all have that monolith app that we've inherited. Well, we have one too, and it's getting pretty big. Our systems are mostly on-prem, spread across our 2 data centers. As far as Innova, if you'd like to know more about Innova, come speak to myself or Sri at some point during the day. It's an awesome place to work. They have a lot of cool things going on there. They're very involved in the tech community, as well as the community in general, so we can tell you all about that if you're interested. So back to business. What should you expect from this presentation? What are we going to cover today? What will we be talking about? We're going to focus on a low-impact, schema-resilient database auditing pattern that we developed at Innova. We call it Audit Star. We'll go into why we developed Audit Star and what some of the key benefits were. We'll talk about the design considerations that ultimately led to a number of trade-offs we needed to make the solution viable. Sri will go into more details in terms of the performance evaluation that was performed as we did the design and implementation. He has a couple of short demos that we'll do as well. And then we'll talk about what's next for future optimizations for Audit Star. We should have a good 10 minutes or so left at the end, if all goes as planned, to handle comments and questions. So why did we build Audit Star? There were a number of business drivers and a number of technical drivers. From the business side, being a financial company and dealing with lending money, there's a lot of compliance and auditability concerns around the SEC, CFPB, as well as our private customers and private banks. A big part of that is securitization. As we lend money, those loans become collateral for raising additional cash to create new loans. So it's very important that we're able to provide a clean audit trail of everything that happens around our loans to show which ones have the best pedigree, which ones did not require extensions, which ones are being paid on time. And the only way to do that is basically to audit your entire system. In terms of technical drivers, it's probably the same reasons that all of you have built your auditing systems. We have a ton of databases. A lot of them were lacking coverage in terms of auditing. Some had different auditing systems, somewhat hodgepodge. So we did have a desire to standardize. We don't want to have our 10 or 20 teams using 5 or 6 different auditing patterns. It's more code to maintain, and it's harder for the team members to switch between teams when everybody does things differently. And then, of course, being techies, we've done this before. We wanted to look at current technologies and say, hey, how can we do this better? We've done auditing before. Can we do it better now with this version of Postgres or with some of the new tools that have become available? And obviously, your auditing solution usually runs a few thousand times a second at a minimum, so we want to make sure that we get it right. So Sri is going to go into more detailed design aspects of it, but just to give you a context of what we're talking about. And most of you have probably built similar systems before, so you're probably very familiar with it. But when you're building an auditing system, you typically have a source table shown here in blue, and some type of trigger that's going to capture the inserts, updates, and deletes and put them in an audit table for you. Some of the patterns we've seen is where the source table and the audit table have all the same columns. But that becomes very tedious because every time you alter your schema for your source table, you also have to update your trigger and update your audit table. And then if you're dealing with devs that don't really care about databases and auditing and working with their ORMs, they don't want to hear anything about it, so they don't want to do any extra work. The other pattern we've seen is where there's a more generic audit table that maybe has two key columns, key value pairs, so the schema on that audit table doesn't change, but when you're inserting a row into your source system, let's say your source table has 20 columns, those 20 columns become 20 rows in your audit table. So when it comes time to use that audit data, you have to stitch that data back together. That becomes very cumbersome, becomes very inefficient. So what we wanted to do was change that a little bit. What we wanted to do was take all the columns in the source table and have our trigger combine them into a JSON object and store the audit information we need as a single JSON column or JSON-B column, depending on the version, in our audit table. Once you get this working, your audit table never changes. As soon as new columns come into existence in your source table, the trigger automatically consumes them, automatically rolls them into the JSON object, and automatically stores them. So once you get here, you're in pretty good shape, but you might think, well, now my audit data is in a JSON object, so my SQL's a little different to get it out. And in addition to that, we kind of did some optimizations on how we store that JSON object. So to make it friendly to the users, we've added a layer on this. We added actually 3 different views that let the user look at the audit table in more of a tabular fashion. And the 3 different views give them different options on how to utilize that data. It makes it very, very user-friendly. So by the time you get here, maybe you like what you see so far, but then you realize I have to deploy this across a few hundred or a few thousand tables across n number of databases, and that's going to be a pain. Do I really want to do that? I've got triggers, I've got views, I've got audit tables. It's a lot of work. So part of the solution is a deployment utility. It's literally a one-liner. We started off doing it as a gem for Rails migrations, but now it's compiled in Go, can be compiled for most any platform, and it's literally one line. It's idempotent, so when you do a deployment or redeploy, it's all the same thing. It figures out what tables are already being audited and which are not, and it will go and add the audit tables and audit triggers where they're missing and refresh the views, and it's no brain power. It's a one-liner. It's basically an easy button for doing the deployments. So, sounds pretty simple. So what could go wrong? Famous last words, right? Sri and I didn't want to burn the place down when we released this. We were a little bit concerned. This seems simple, but since it touches almost every table in the database, the code's going to run a lot. What I did skip over in a previous slide for the deployments, obviously, as you're deploying this across an entire database, there may be some exceptions where you want to skip a few tables that you know you don't want to audit, or a few schemas even that you don't want to audit. So we actually added the ability to put that in a config file so that you can skip select objects. So given that, when we go to do the deploy, we're really touching almost everything in the database. So we did lots and lots of testing. Lots of tuning, trying to get the triggers just right. Lots of benchmarking to figure out how to optimize the creation of the JSON object and which data and which diff to store. We did full-blown exercises with database snapshots where we wrote routines to touch and tickle every single table to figure out what we were missing and what could possibly go wrong. We built a regression suite, did manual testing, and of course did a phased rollout across our different databases. And believe it or not, by the time we got to the second one, we ran into a bump with inheritance and had to make a change. But as we slowly rolled it out, we worked out a lot of the kinks. So what did we get from this? We've touched on these points so far, but the key benefits summarized here is that we're capturing the historical data, which was our original intent. Our DDL changes are now non-breaking for our audit system. We're not doing any maintenance. Nobody's writing custom code when they use our solution with their database or as they change their database. There's virtually no maintenance required. And a lot of this comes from using JSON, that JSON construct, to capture the data in a semi-structured format. Then to make this solution viable, we went the extra step and created the views to improve accessibility. And we created the utilities to make the deployment easy. We also did a lot of optimization with respect to the transaction overhead created by the system, and also optimized it with respect to the amount of disk space used. In addition to rolling out an auditing system, almost in parallel, we're rolling out an archive and pruning system that would take older data from the auditing system and move it offline to another data store so that it wouldn't continue to build up as we use the system. So going back to the design for a sec, remember that we wanted to meet the basic auditing need. We wanted the pattern to be resilient to schema changes, zero impact, zero maintenance, easy to deploy, user-friendly. This is what we wanted, but as we tried to implement it, all of these things came at a cost. Every line of code that we wrote made the solution more complex, affected the performance of the trigger, impacted the size of the database, increased the risk that something would break. So we're in a constant battle of design considerations and trade-offs, figuring out how to optimize this solution so that we'd be confident deploying it against n number of databases at Innova. So now I'd like to invite Sri up here. He's going to talk a little bit more about the design iterations, the benchmarking that was done, and provide some demos to give you a more clear picture on how this system works.
Thank you, Sam. Okay, so like Sam was saying, since this is going to go out to like pretty much every system we have, and some of our systems have throughputs in like the tens of thousands of transactions per second range, we wanted to make sure that this is something that is cool for us to write, easy for us to maintain, but also doesn't adversely affect our business in any way. Right? So we kind of split our design considerations into three: time, space, and maintenance. And I'm going to go over like the iteration for each one of those before doing the demos. So first, when we wrote this, it was really cool, and that was a mistake. So we auto-partitioned itself. It would make child tables as new data came in, making it easy to prune. It had indexes just to high heaven. And it cost 100% slowdown, right? Like everything, like transaction rates were cut. Obviously, when you're indexing everything and storing copies of everything in your index, things get bloated and things get slow. So finally, like when we realized that this was happening, we reverted back to the basics and made something that is like that simple, because ultimately that's the thing that scales. Right? Like when you make something that's really cool, it's nice as a toy, but when you put it out in production, not so much. So the final avatar, much less cooler, had no partitioning. It had like one index on it, and we'll go into like details as to why, but it ran twice as fast. And then there was space. So initially we captured everything, right? Like the client query. Imagine if you turned on like full query logging inside your database. Right? In retrospect, that sounds like a really ridiculous idea. I thought it was really cool, and I did it, and it was not good. So we captured everything, like who made the change, where it came from, the IP, the port, like what the query was, every parameter we could probably lay our hands on. We made that fully redundant by logging that on, like logging inserts, just in case. Oh, what if you prune the data? Yeah, didn't go down well with our database administration. So finally, we reverted that to only capture the changes. And all of these things that I'm talking about will probably become way more clearer when we do the demo. But yeah, so we only captured the things that changed, left out the parts that didn't. We did not capture data that was inserted, so we did a lot of analysis on our workloads. So it turns out that we are like very insert heavy. So like pretty much a lot of the transactional systems out there, we get all the data, put it in there, and then never want to get rid of it. So we have a lot of inserts, some updates, but once you start capturing the inserts, you basically have full redundancy, right? You have your insert and then a copy of it, and then you have another insert and a copy of it. So we realized that there's no need for that, and in fact, we can move the smarts for doing something like that into views, and we'll go into like how we do that. Yeah, so, and then finally, uptime or maintenance. So the first avatar was like completely safe because I didn't want to get woken up at 3 in the morning because the auditing system had broken the transactional system, right? So I was like, I'm just going to like put exception blocks all over the place, make sure that no matter what happens, the OLTP system can run fine, right? And the auditing system will deal with it in the morning. So it turns out that that's not auditing anymore, right? Because you're making changes that you're not capturing. So if you want to do true auditing, you cannot let the change get through unless you capture it, right? So if it breaks, we should break our database, right? And so that made the problem a lot more, I want to say significant, right? Like it raised my hair, or it gave me goosebumps. So I was like, okay, so this is like live, right? There's no escape hatch, so you got to get it right. So this was an interesting trade-off because we basically, locked ourselves into a room and said that, well, if we don't find our way out, we're going to die. So yeah, it worked out. So how did we test all of this, right? So PGBench, that's the standard. For those of you who don't know, PGBench is like the standard benchmarking utility. And we picked TPC-B. So there are different benchmarks in the benchmark standards that are published. There's TPC-A, B, C, H. H is a pretty common one. You've probably heard a lot about it yesterday. So B is a database stress test. It basically parallelizes the number of connections it can make to your server and then beats the hell out of your database. It's trying to measure how many transactions you're getting and how much slowdown you're causing because of changes that you're making. So, which is perfect for us because that's what we're doing. And so what we did was, well, let's just make different avatars of every function there is, right? So this whole auditing thing boils down to the trigger function because that's the thing that is actually doing the auditing, right? You have a table, you have a trigger function, and then you have another table where you're going to capture the changes, right? So the heart of the logic is in that trigger function. So I just need to modify the trigger function in different ways and see how it behaves, right? So we had, I want to say like about 30 odd iterations or flavors of trigger functions, just kind of like getting a feel because, and the results over here, I'm going to go over them in a second, are applicable only in the vacuum in which we did our tests, right? Because these are our databases, this is our hardware with our settings. Everything is configured and tuned for our business. So whatever you see here, take that with a grain of salt, right? Like this is not canon, it's not the Bible. You don't have to like take this away and be like, somebody told me that this is going to happen, so don't do that. No, try and figure, like, what I'm trying to say is that benchmark, right? And that will tell you, don't guess. And we did, and we found out why all the mistakes that we're making. So what we found out for our workloads with our tuning is that a B-tree index costs about 10% TPS. A GIN index or a GIST index over JSON-B, that's about 80% TPS. That will kill your transaction. If you care about your transactional, like your throughput, that's a surefire way to kill it. Make 3-4 of those and exception blocks or save points. So for those of you who don't know, exception blocks are basically like try catches or begin rescues. I don't know all the flavors of them. In PLPGSQL or any of the stored language procedural languages inside Postgres. So exception blocks cost around 4%, but at the risk of failing audit, right? Which is we could rescue from an exception that the trigger function is throwing up, but we won't log the change. So what good is an audit system that works sometimes, right? Dynamic SQL, and this one's important, it costs about 30% TPS for simple inserts, right? So this is one common area, I feel, where a lot of people overlook things because you have to write the trigger function every time for every table. As engineers, we are very incentivized to, be lazy. So what we do is we make a function that'll work for everything. And the way that works is you have to stitch together strings and execute it, right? That's going to cost you a lot, right? In fact, for us, it cost us 30% in transaction throughput. which was not something we were ready to live with. So we did the same thing. I mean, I'm still lazy, so I didn't want to write the trigger functions over and over again. So instead, I molded them, right? I made a mold, and then I just put the values I needed, and I repeated the trigger functions. These are not things that anyone wants to look at, right? So I can script them, but what I'm saying is that don't script them once, right? Don't write a generic trigger function that executes SQL. I remember that in Postgres, I want to say Postgres opened 2014 or 15, there was a person who did analysis on how expensive trigger functions get with if you have like conditional blocks in them versus dynamic SQL. And the inflection point is very far away. I want to say it's like after about like 4,000 control branches, it gets more expensive to have control versus having dynamic SQL. So dynamic SQL, not your best friend when you care about performance. If you don't care about performance, it's just like, it's a whatever thing, like, you have your pet project on the side, yeah, go ahead. And then finally, the overhead of JSON itself. So JSON and JSONB, they are amazing features, but sometimes misunderstood. JSONB is binary JSON. That means that when it's being marshaled and stored inside the database, it's being stored in binary format, which is expensive, right? If you store JSON, it's just string, like, making its way straight through to the database. But JSONB, there's a conversion, and it has to pad and do all of its things to store it. And that is expensive, right? Because you pay the upfront cost to convert it to JSON so that you don't have to pay the cost when you read it. Versus with JSON, where you actually store it and you don't pay the cost, but then you pay the cost when you read it, right? So it's just amortization. If you want to take the cost every time you read, take the cost. Or if you don't want to, then just store it the way you want it, and then you don't take the cost when you read it. But the bottom line is that JSONB is expensive, both in space and time, right? It takes more space in the database because you need more space to represent the structure of JSON, and it takes more time because, well, you need time to do that, right? So that's expensive. Now, the fun part is that this kind of has, so I feel cliche saying that space and time are kind of correlated, but if you store more data, it's going to take more time, right? And space, obviously, but more time, because you have to take more time to marshal all that data, right? So the redundancy that we were talking about of just storing the row every time, the whole row, oh, it changed from all of this to all of this, and from all of this to all of this, that's going to cost in JSON marshaling, right? So not only in space, but also in time. So finally, the product that we have out live right now that we settled on, the throughput overhead is about 30%. This is averaged over like all the tables that we have. Remember that there is going to be an overhead, right? It's impossible to avoid the overhead, because what you're saying is that every time I make a modification operation, I'm going to insert a row, right? This is not free, right? So there is going to be an overhead nevertheless. We can minimize it. So 30% is what we have based on the different sizes of rows being inserted, different updates being made, sizes of the table, size of the data, et cetera. So we are sitting at around 30%, which we're OK with. The space requirements, it's about 80 bytes by itself for all the data that we store, like metadata in terms of time and who made the change, et cetera, all the way down to like the internal data that is being stored behind the scenes in the table. There's a bunch of it. There's like, I'm not going to go into specifics right now, but there is some internal data backing every row, plus what we have is about 80 bytes, plus the size of the primary key itself, converted to text, plus 2 times the size of the JSON diff, which was a formula that we were OK with. And like for all intents and purposes, we have not seen our databases grow in size going this way to this way, right? There's an uptick, but it's like the slope has not changed significantly. OK, so let's go into the demo. And I'm just going to do a little quick revision of exactly what you're going to see. So this system is like having a shadow copy of your database running within your database, right? There are multiple audit systems out there. You can have audit systems that do offline auditing, like in log files. And there is PG audit, which is something very similar to that. So it depends on what you want. What we wanted was this to be in our database because we needed it to be live for multiple purposes. Debugging is one big purpose. And the second one is that given that it is live in our database, it's easy for us to leverage the power of querying that we have over our data to join back to the auditing itself, right? Like if I just want to look at everything that changed about a certain product or a certain like section of the data that I care about, I can index into that from my transactional OLTP system as it is, and then join to the auditing system because the auditing system is just a set of tables within the database, right? So that power of having them in the same place is quite big. So what it looks like is that you have a bunch of schemas, like those are just example schemas there, and then there are audit schemas, the ones all the way on the right, which are just shadows of those schemas, and then there are views in between which kind of couple both of those together and present the whole picture of that for you. So what that kind of looks like is that, say you had an object, right, and then you have the auditing system, right? Every time you make a change, there is a shadow of that object that is being stored somewhere within your database, right? And then you have a view that is going to put both of those things together and present the whole picture of the object with its history for you, right? So it's like you have the object as it has traveled in time within your database for you. So what that looks like in terms of like the actual table is that, so I'm just going to consider a really simple table called brands. And so say you have a simple table called brands with like one field in it that we care about, brand, or a couple of fields who updated the brand, for example, right? Then your audit table has a bunch of data, which is metadata, and then it has the two or three main fields, which is the primary key of the table that it is auditing, and the data before it changed and the change itself, right? And both of those columns are JSON, which means that it is, like Sam was saying, agnostic of the schema of the table itself, right? And we'll show this as we go through the demo. So we took these two and then built a view on top of it, right? And in fact, we have three views, as Sam was saying, which kind of show you like different avatars of the same thing, which is how did this object travel in time? What did it change from? What did it change to? Give me snapshots of it, or give me just the changes, the deltas as they happened, right? OK, so enough talking. I'm going to do a simple demo for you now. OK, so I have my database set up. And I will list all my schemas first, right? And as you can see, there is, for basically every schema, there's like a shadow of it. So you have a backfill schema, and then there's an audit schema, which is the views, and then a raw schema, which is the actual data, right? And that happens every time, right? So this schema explosion was something that we were considering, and for multiple purposes, we went into this. The chief of those being name collisions, right? If you try to like put everything into one place, you kind of defeat the purpose of why you split them out in the first place. So that's why we have we let each thing be its own thing instead of making one audit schema with one table in it, which has all the data, right? So we're going to deal with this table called brands. So let's see here. Right, we have just a few brands in there, just some simple brands. These are brands that our company deals with. So first, I'm going to show you that there is no data in the audit table. It's empty. It's got nothing, right? And now let us. OK. All right, I can't read that. I can read that now. OK, so simple operation. I'm going to perform an insert. I inserted data, and there it is, right? But as you can see, there is no data, right? Because the data is in the parent table. Why would I capture the data again if it's already there, right? So I just logged that there is an insert that happened, but I didn't log what I inserted because nothing has changed about what I've inserted yet, right? But if I go ahead and update this, now I have a copy of what changed, right? But this is JSON. So as you can see, what it was before the change. And maybe I should shrink this a little bit so you guys can see the. OK, yeah. So you can see that before change, the brand was Samsung, and then it changed to Sung, right? And there's only that captured there for you. But this is where we leveraged views to actually make apparent what data was inserted and what was changed. So instead of going into the raw schema, if I just go to the normal schema and then say, I want to see a snapshot, right? And there are 3 views. Actually, there is compare, snapshot, and delta. And these 3 views are organized in increasing order of data they give you and decreasing order of performance, right? So delta is just deltas of what changed. Snapshots are just a snapshot in time of the row as it changed over time. And then compare is like the row as it was before that point of time and after that point of time. As it was before, as it was after, for every operation that got performed. So as you can see, each like delta to snapshot to compare has more data in it, but it also has less performance because there is more stitching that needs to be done. And we'll go into what that stitching is in a bit. So if I just want to see a snapshot, which is like, I want to see how things changed in time for this, I can see, or sorry, I want to see how the row evolved over time. I can see that first, okay, that's not good. It looks nicer when it's a single row. OK, there we go. So you can see that I inserted the brand as Samsung with the ID 8, right? And then I updated the brand. It changed. At this point in time, it was just Sung with the ID 8. And then now I'm just going to go ahead and delete that, right? And then do the same thing. And then you can see that it went away. But you can see that even though the data has been deleted, which means it's no longer in the parent table, I'm able to reproduce it. Right? I can say that it was Samsung when it was inserted, but it's not here. But that's because it's now captured here, right? So when you delete the record, that's when the record goes away. Now I have a copy of the record before it went away, just in case, right? So we don't perform that many delete operations. I don't know about, I mean, there are workloads or systems out there which are probably churning data, like putting them in and getting them out. But we are a financial, like a transactional company, and most transactional companies treasure their data, even in their transactional databases. They don't want to get rid of anything, right? Just in case. Which I'm not promoting that. I'm not saying that's a good thing, but mostly data goes in there, sits there, and then never goes away. So in case you did get rid of it, right, that's when we make a record of it, right? And this is, again, optimized to our workload, which is we don't delete things. Or not very often. So we insert it, and we inserted it, we didn't make a copy of it, right? So for the bulk of our operations, it's not going to be inserted, or it's going to take no space in the database. But when you delete it, yeah, then I'll make a record of it so that I can tell you what you deleted, right? So that's how we're able to see what it was, even though it's not there anymore. So, yeah. And I'm going to do some simple operations. So we kept talking about like how this is schema agnostic, right? Which is you can add a column and then it'll be fine, right? So let's see how that behaves. So I'm going to alter this table, right? This brands table, and I'm going to add a column. And just for fun, since it's JSON, I'm going to add a column which is JSON, and let's see what JSON looks like within JSON, right? So I added a column, right? It's a JSON-B column, and then I'm going to go ahead and oh, I forgot. I have to put this data back in. So my insert statement there is. OK. And let's see what that looks like. Right? And you can see that, well, the description was nothing before. We added a description column. And now it just seamlessly captures it because it's just JSON. Right? There are no columns. It's not statically typed against the structure of the table. It's JSON. It's unstructured. Right? And this we do a lot. Right? At our company, we roll out migrations, or we change the structure of the database at the drop of a hat, which is not a great thing, but it's a thing. So we just have to live with it. And so since we can't police and be like, oh, wait, you're making this change, so you got to make sure you do this other thing. And We didn't want to have the overhead, like Sam was saying, of maintaining this trigger function every time. We just wanted to make sure that no matter what happened, we had the copy of the data, right? And that's why we chose JSON. As you can see, it works. I didn't do anything. I just altered the table and then ran the thing. Still captures the data, right? The views don't work well yet because the views are created in the images of the table, right? So if I actually try to select from the view, you won't see any of the descriptions, right? Because it's created in the image table. So how do we do all of this view magic and everything? So when we were looking at this at the beginning, it was really complicated. So we were like, OK, so we have this table, right? I made an insert operation. And then I changed the data for A from 1 to 3. So I captured that change, and I deleted it. And I need it to look like that. How? So clearly, well, you see that the insert operation should make sure that the old values are null. And then the new operation gets its values from A and B if it's an insert. And then if there is a before change, then it has to come from here. And then if it's really complicated, right? And in fact, it turns out that there's a very nice pattern for this. And I'm going to show you that pattern over here. So the formula is those two things. It's kind of like a sieve. The way I think of it is that looking at your data top down, right? What that means is, so the formula on top is complicated, so just ignore that. So how did I get that A was 1 when I inserted the data, right? Corresponding to every operation, I'm going to go to the audit table, right? And I'm going to look to see if I have the data as it was before the change, right? Do I have a copy of a JSON with it mentioning A before it changed? No, I don't. Then start looking downwards until you find a mention of someone changing A, because that's what A was before it changed, right? So hidden within all of this auditing system, and this is where we move the smarts so that we can have compressed auditing. So we're capturing less data, and we are saving on our throughput. There's a trail, right? And that trail comes from basically looking through your data to find the first instant at which it changed. When you inserted the data, it didn't change because there was nothing to change, right? But then at some point in time in the future, when we changed A from 1 to 3, it changed, and that's where it changed, right? So A went at the update operation from 1 to 3. And thus, that is what we inserted, right? And that same formula holds for everything, right? It's the same thing. You go all the way through and try to find what the data was when it changed. And if you can't find it, then keep looking downwards until you find the time at which it changed, right? And there's a really nice side effect or benefit that you get from this. So when you start auditing this, or auditing your databases, your heavily churned tables are going to accumulate audit at a rapid pace, right? Which means that at some point, you're going to have to jettison that data into your warehouse, right? So if I jettison the data, I risk losing this trail. So how am I going to reconstruct it? Well, so the cool part is that as humans, we jettison data that is old, right? Which means that we jettison data upwards. That is, the oldest data goes first. But since we're looking down, that doesn't affect us, right? Because I don't depend on the old state. I depend on the next state, right? So I can actually get rid of rows and still tell you what the state of the row looked like going down. And I can show you a little demo of this too, right? So let's go to that. Oops. OK, sorry, I messed up the order of the slides. OK, so if I go in here, right, and I'm just going to delete, so I'm going to delete the row from the audit system, which it won't let me do because the audit system is tied down. And I can't do this in production, but I can do this now because it is my database. I'm going to disable all the triggers. I'm going to delete. Say I delete. So as you can see, there was an insert operation, like operation number 4, right, which is saying, oh, I haven't shown you a couple of things. Let me do this over again, because this is just going to get really complicated. Oh, one sec. I have to reset my database so that I don't. Okay, here. Okay, so I'm going to perform the simple operations that I performed all the way at the beginning. So I'm going to insert some data, right? And then I'm going to update it, and then I'm going to delete it. But let's hold off on the delete, because that'll make it too easy, right? So I have inserted data and then updated it. So now if I go through my audit trail, right, I see that I have Samsung inserted and then sung when it changed from Samsung to sung, right? I'm just going to go ahead and delete the change that I made. So I'm going to disable the triggers, and I'm going to delete that. I'm going to query this. It still shows me the best of what it can, because starting from that point, it is only looking downwards, right? It doesn't depend on what I deleted because of the pattern that we just found. So that's something nice that we just found as an after effect. So this allows us to prune our entire auditing system in all our databases without having to care about whether or not that would affect the views that are constructed on top of it. There are a few other destructive DDL operations that I can probably show you, but I don't have a lot of time left for that. So I'm going to stop here. If you guys care more about this, I'm just going to point back 1 second to. Okay. Go back. So it's soon going to be available in our open source repository. It's GitHub/Innova/AuditStar. It is right now living in our enterprise Git. We do a little bit of crafting on it before we put it out into open source land. So you're welcome to open the code, go through it, see how it works, and you can test it out. And I just want to finish off with some possible future optimizations, because no system is complete unless it has a future to evolve to. So 3 things that possibly that I could think of. One, Brin indices. Brin indexes are very cool in that they are very cheap in terms of construction cost and disks, so in space and in time, because they only index data every so often. And that's a 9.5 feature. All of our databases are not on 9.5 yet. So that's a really cool feature that you can put on time, right? So you can ask questions like, well, I want to see all the changes that happen to this thing between this time and this time, right? And if you try and index time, time has it's mostly a monotonically increasing field, which means it'll have no overlap, right? There are no ties, and there are very little ties in time. So if you index it, it'll be very expensive. And as we saw, the indexing cost of B-tree is about 10 to 20%, or around 10%. So we don't want to take that cost. Instead, we just want to wait for 9.5, where we could index Brin. Brin is a lossy index, but that's good enough for us, because the pages are all we need. So Brin, that's one optimization that we're waiting for once we get there. Second one, and this is a really big one for us, which is coming in Postgres 10, transition tables for triggers. So right now, all the trigger functions, they are written on a per row basis, which is very expensive, because when you context switch, it's expensive. That's what causes the overhead, right? So when you do batch operations, you update 10,000 rows, you're making 10,000 context switches, right? And that adds up and slows down your transactions. And the reason you have to do this is because after statements in Postgres don't give you access to what the changes were before and after until Postgres 10. In Postgres 10, you're going to get all of that data in tables, right? So your after statement is going to give you, well, this is all the rows that changed as they were before and after. And as we all know, set theory, we love batch operations. So when you have all of that in one shot, you just have to context switch once at the very end and log all of it, right? And that's always way more performant. So that's one thing that we're very excited about and we're waiting for in Postgres 10. When we're going to get there, I don't know. But when we get there, we will use it. And then finally, the views, they are not very schema resilient in certain cases of like destructive DDL. But again, these are just the views. The audit system by itself is fully schema resilient. It's the views which are and it's possible to make them schema resilient. We just didn't invest a lot of time in that because we were not very concerned about it back then. But yeah, those are some future optimizations. If you have any questions, me and Sam would be glad to take them right now. Absolutely. Okay. So the question was, how does the implementation compare with a temporal database? So there's actually someone sitting here in the first row who is going to be giving a talk on that today. I sincerely urge you to go and hear that talk. In one statement, I can say that temporal databases are a superset of what this does. This is only looking back in time. Temporal databases have a fluid concept of time that goes back and forward in time. And the way you store the data in the temporal database is also different because here we store the data in a separate table. Temporal databases have the data in the same table, which has advantages when it comes to certain kinds of workloads and disadvantages in certain other workloads. It's a deep question. It's a great question. I can't answer that fully. I would say go to that talk and maybe ask her the question and she'll answer it.
Can I ask you a question?
Yes.
All right. So my first question, how do you use your audit table? Because like I know more than anybody in this room why you chose to go with JSON storage.
Right, right.
However, the max you can like literally go like on single like pointed queries. What happened at this time? So basically, you at large you should be unable to efficiently run like any sensible select. So what's the use case for this except of later kind of expanding it to the data mart?
Okay. So the question was, like, when you want to do some sort of forensics and you want to go to a certain point in time, it gets more expensive as you accumulate more data. So exactly how do you use the auditing system? It's a great question. And so there is a field in here called primary key, right? And that primary key is a text representation of the primary key in the row itself, in the table itself, right? And that's all we use to tie the data together.
Okay.
That's it.
So you do not really search by anything else?
No, no, no. Yeah, we could. So at the beginning, we did try to index JSON so that people could answer. Yeah, yeah.
I know, that's why I asked.
Very expensive.
I know.
Yeah. So with that, we do only in our marts. You're right.
Okay. And do you like you only have like plans to kind of parse it to the data mart, or you really do this?
No, we are doing this to our data mart right now. So that's the other really nice thing about this. So everyone who has an ETL process knows that as your OLTP system changes, your data mart has to stay up to date, which is very painful. And so this never changes.
Yeah, but I mean, they got to change it, they got to change it.
Correct, yeah. So if you want to cost this ultimately, so all of that data that is being represented in JSON is text representation, right? Which means you have to like convert that to a native type ultimately. And that is what the views do. So everything that you see in here, brand ID is an integer and brand is a text. And I know that because I'm taking the raw data, the JSON data, and recasting it to whatever the table's types are right now. So I'm re-imaging the data in the image of the table, right? And that they have to do on the data mart, or they have to live with just text representation.
So basically, at large, it's kind of like just the means to push this data to the data mart.
Yep, yep.
Doesn't really do anything sensible.
No, in our transactional systems, we just use it for some sort of like forensics. Oh, why did this break? What was the state of this before it broke? Why did the state change not happen? Right, that's it.
And that's the last thing that happened. So you mentioned you did not want to do the dynamic SQL. So basically, am I right? You have like the generators to create
Yep.
the trigger
Yep.
functions for
Yep.
each table.
Exactly.
Okay,
That's it.
Thank you.
So if I want to know when a column changed to a certain value, I have to wait until it gets to the mark.
Yep. Yeah, because like if you, well, let's put it this way. If you want to know in a reasonable amount of time, yes, because combing through all this JSON is going to be very expensive. Sorry, we have no more time for questions, but me and Sam are going to be around. Sam longer than me, and feel free to find one of us, and we will be happy to go into depth with this, with any questions you have. And that's it. Thank you very much.